Yeah, 170, and then like 79, and then 1.
Are we gonna end up making it to the test by Friday, or?
Oh yeah, today, tomorrow, there's only 2 sections left.
I could only go until like 10, 15, 10, 15, like 10, 15. Because I got in trouble.
Okay, so far in this chapter, we've done hypothesis testing for the difference between population means for large samples and small samples, but of independent samples. One sample didn't affect the other one at all. So now this section is hypothesis testing the difference for dependent samples. Has nothing to do with sample size, but dependent samples. Or dependent samples. So what makes samples dependent?
One affects the other.
One affects the other. In this case, it's pretty much paired data. It's the same group of people, like a before and after kind of thing. So for dependent samples, in this case, each member of one sample corresponds to a member in the second sample. So no longer will our two sample sizes be different, they'll be the same sample. So we're first just going to look at two situations where I've got independent samples, you can see the difference, and then where I've got dependent samples, just so you can wrap your brain around that. Are the two samples independent or dependent?
I have 3 lines.
You can fit this on 3 lines.
How do you? Okay.
Independent or dependent? Here's our first sample. Let's take your midterm for 16 chem students, and then the final exam. For the same 16 chem students. Are those two samples independent or dependent?
They take into account how much they studied.
Doesn't matter, I'm just looking at their scores. I've got the 16 scores on their midterm, I've got the 16 scores on their final exam. Are those two samples independent of each other or dependent on each other? What'd you say? You're wrong. Independent, one doesn't have any impact on the other one. These are the same 16 people. Of course I'm going to impact myself. So when it's the same group of people, that's automatically dependent. I don't care what the scores were. It doesn't matter what the scores were. The fact that these are the same people makes them dependent. Dependent. I think you know what's coming here, but let's take a look. Let's take the height of 30 males, and we'll take the height of 30 females. Are those two sets of data independent or dependent? Definitely independent. There's no overlap. When the whole point of this section is, I'm pretty much looking at a before and after. So these are independent. Okay. So the situations that have to happen here, okay, sample size is not an issue. This will always be a t-distribution. Always. So dependent samples It's always a T distribution, no Z's. Okay, so when do I do this? Samples? Yes. So samples have to be paired. Both populations have to be normally distributed. Your test statistic
For those six, normally can't do it.
correct. Your test statistic is, they call it, they have a special name for it, it's the difference between the sample means. But they call it D-bar. Well, it's actually the average difference between the sample means. So your test statistic is called D-bar. And what you're going to do is the average the difference. You're going to take each X value and subtract, like the before minus the after. Add all of those up, and then divide by your sample size. Sum, add up, sigma, add them all up.
I hated that. Oh my gosh.
Yeah.
Wait, what else are you adding up? You said the X one last week too.
Yeah, but if I had, like, say the 16 midterms and the 16 final exams, I want the difference between, like, how I did on my midterms and then how I did on my final exam. I find that difference. Each person, your difference, and then we average all those differences together. So that's what we're doing here. That's going to be your test statistic. That's what you're going to see if it's in the shaded region or the unshaded region. So you're going to have to find this. Okay? And then to turn D-bar into a T-score, the T-score for D-bar is D-bar minus the population difference. That'll be in your hope over the standard deviation over the square root of the sample size. Okay, so let's try one. We've got by hand, by program, and a confidence interval. Ready? Where's my book? It's over there. We're doing try number 2. Okay, we've got a physician claims that an experimental medication increases an individual's heart rate. So the claim is that this particular medication increases heart rate. Oh, it is example 2. Okay, 12 test subjects are randomly selected and the heart rate is measured. The subjects are then injected with the medication. After 1 hour, the heart rate is measured again. The results are listed at the left. Assuming heart rates are normally distributed, heart rates are normally distributed. Is there enough evidence to support the physician's claim at alpha equals 5%? And then I'm not going to make you copy all this data down. I'm going to tell you you're going to need your book in here in a minute. It's on page 393. We'll get to that in a second. We'll write our claim. Okay, so we are looking at before the medication is administered and after. So if I do the average before, well, if it increases, how can I write this? If medication increases heart rate, what's the before compared to the after? Less than. So the before heart rate is smaller than the after heart rate. Could I switch this around and say after is bigger than before? Absolutely. So there's always two ways to write these. And we're doing the difference. So that means the average before minus the average after is less than 0. Okay. So there's our HA. That's our claim. So the average before minus the average after is greater than or equal to 0 is the hope. Okay, so what tail test are we doing? Left tail test. %, shaded. I need a t-value here. Oh, I forgot to, I missed a, I knew I missed something. The degrees of freedom. Forgot to put it back here. You want to squeeze it in here. Degrees of freedom. Okay, because it's essentially the same sample, just you're using that same sample twice, it's just going to be n-1. So, our sample had 12 test subjects, so our sample size is 12. So that means our degrees of freedom is 11. So our DF is going to be 11. Our alpha is 0.05, and I'm in the left tail. You can use the table, or you can use your MC if you have it. Negative what? You were wrong on your homework. Are you right here? Anybody agree with that? Okay, concur. All right. So now the work comes in. Now we have to do this D-bar business. What we're going to, the quick way to do this is going to be to use a list, because I need to take each before minus after, add them all up, and then divide by how many I have. The list will make this a less painful process. So, finding D-bar. We'll write out the steps here just one time. So we're going to enter before data into L1. We'll enter the after data into L2.